Hi guys. So we're continuing our quest to discover how vectors can be used to describe equations of lines. And remember that the motivation for this is that we can easily describe a line in two space with our standard form equations or slope-intercept form equations from grade 10. However, we cannot use those same equations to describe a line in three space, which is important in the study of vectors. So let's just have a look at the vector equation of a line, because the next topic, which is the parametric equations of a line, is described from that form. So the vector equation of a line, just to recap, this is in your textbook, is r equals r naught plus t times m, where r naught is any position vector that ends in a point on the line. M is any direction vector that describes the line, meaning parallel to it. And t is just a parameter, so any real number. Now, since r is a vector, in general, we can write it as xy, with x and y being the components of that vector. And since we're using xy for r, let's use x naught, y naught for r naught. And let's use m1, m2 to describe the vector, the direction vector m. And when we do that, we can then easily we can then write the vector equation of a line as xy is equal to the vector x naught plus the parameter t times the direction vector m1, m2. From there, we can easily rearrange and derive our parametric equations of a line. And this is just another form for the equation of a line described by vectors, just like we have multiple forms for standard form of an equation, point-slope form, and slope-intercept form from before. And so the parametric equations, I'm just going to go on the next page here. We're going to take the first component of vector r and make it equal to the first component of vector r naught plus t times the first component of the direction vector. And then we'll do the same for y. So these equations here are known as the parametric equations of a line in two space. And as you can imagine, we can easily extend it to three space by simply adding a third component to each of those vectors. And so z would be equal to z naught plus t m3, where m1, m2, m3 is the direction vector, x naught, y naught, z naught is the position vector of a vector in three dimensions. Sorry, of a line in three dimensions. Okay, but we'll come back to the three space. Right now I just want to look at example 2 on page 432 in your textbook, which is an example with parametric equations of a line. And so it says, consider the line L1 given in parametric form, where x is equal to 3 plus 2t and y is equal to negative 5 plus 4t. Part A asks us to find the coordinates of 2 points on the line. So we know that, I'm going to just fix this 2 here. We know that one of the points must be 3, negative 5, because those are the coordinates of x naught, y naught, which is a position vector for the line, and the position vector always ends in a point on the line. So call that P1, that's one point on the line. Another point on the line we can simply get by choosing any value for the parameter t. And notice that this point would work for the parameter t equals 0, because then we just get rid of the second terms in both equations for x and y. So let's just let t equal 1, and then we're going to get another point on the line, which would be 3 plus 2 times 1 for x, which is 5, and negative 5 plus 4, which is negative 1 for y. So another point on the line, P2, is 5, negative 1. Now we want to write the vector equation of this line. The vector equation always starts with vector r equal to vector r naught, which is a position vector for the line. And since we know that both of these 2 points are on the line, P1 and P2, we could do either one of them as a position vector. I'm going to do 2 different lines here, so R1, R2. This is just showing you that there are infinitely many possibilities for the vector equation of a line, because you can use any point, any position vector where that ends in a point on the line, and you can use any direction vector that's parallel to the line. So for R1, I've chosen position vector 3, negative 5. For R2, I've chosen position vector 5, negative 1. And then plus our parameter t times direction vector for the line, which from the parametric equation here we know is 2, 4. But we could use any vector that is parallel to 2, 4, because that would also be a direction vector for the line. And if you think back to collinear vectors, vectors that are on the same line are parallel, and they're also scalar multiples of each other. So one scalar multiple of 2, 4 would be 1, 2. That would also be a possible vector equation for this line. Another possibility would be to use the point 5, negative 1, or find another point altogether by letting the parameter t be 2, for example, or any real number, and use a different scalar multiple of 2, 4. So let's say 8, 16. That would work too. There are infinitely many possibilities. Okay. Part C asks us for the scalar equation of the line. So I'm going to introduce the scalar equation of a line here. Actually, no, I'm not. Sorry, I'm going to skip that for a minute. I'm going to do that in my scalar equation video. So part D, I believe, also has to do with the, no, it doesn't. Okay, so we can do part D. We're skipping part C for now. Part D. Determine if line L1 is parallel to line L2. Okay, so line L2 is x equals 1 plus 3t, and y equals 8 plus 12t. And then just recall that line 1 was x equals 3 plus 2t, and y equals negative 5 plus 4t. So in order to know that the lines are parallel, we would have to know that the direction vectors are parallel. And what I just said in part B was that if the direction vectors are parallel, then they're scalar multiples of each other. So if I can find that direction vector M1 from line 1, for example, can be written as a scalar multiple of direction vector M2 from line 2, for example, or vice versa, then I'll know that these lines are parallel. So the direction vectors are, M1 is 2, 4, and M2 is 3, 12, and I'm getting this from the parametric equations. The numbers that are multiplied by t, those are the components of the direction vectors. So is there any way for me to, any k value that I can choose to make m2 a scalar multiple of m1, or vice versa, it doesn't matter. Let's see. So if this could work, then 3 would be equal to 2k, and 12 would have to be equal to 4k. Well, if from the first equation, k is equal to 3 over 2, or 1.5, from the second equation, k is equal to 3. So since they're not the same, then there is no one parameter that would make these direction vectors scalar multiples of each other, and therefore they're not parallel. K1, let's say, sorry, K, since the K values are not the same, therefore M1, sorry, therefore line 1 is not parallel to line 2. So L1 and L2 are not parallel.